To solve radical equations, what we're going to do is use a process similar to our properties of equality. However, it is a notable difference that it's not truly a property of equality. While it behaves in a similar manner, it is going to cause some side effects that our properties of equality don't necessarily do. We're going to use the power rule, where we can raise both sides of an equation to the same exponent based on whatever the index of the radical is. All the solutions in that new equation, and I do want to emphasize that it is a new equation, all the solutions to the original equation are contained within the set of solutions for the new equation, given that the original equation does actually have solutions. So generally we're going to follow this four-step process, where the first thing we do is isolate a radical. So if we have a radical in our equation, we get it by itself. If we have more than one radical, we pick one of the radicals to isolate. Then what we do is we'll raise each side of the equation to a power equal to whatever the index is. If it's a square root radical, then we'll raise it to the second power. If it's a cube root radical, we'll raise it to the third, and so on. If after we perform that operation, the equation still contains radical terms, we're going to repeat steps 1 and 2 until we have an equation that does not contain any radicals. Then we'll solve the equation based on whatever methods would be appropriate. If we have a linear equation, we can go right into isolating the variable. If we have a quadratic equation, we can set equal to 0, so it's in standard form, and then isolate to solve after we factor. Now, because we are creating a new equation, and the solutions to the original are contained within the new equation, that means that occasionally we will get extraneous solutions. And so our new equation is giving us a set of proposed solutions. We need to verify all of those first before we go and claim that they are solutions to the original equation. So let's take a look at some examples. In our first problem here, we already have a variable isolated. So what we can do is just go straight into the exponentiation. So in order to cancel out the radical, we can raise both sides of our equation to the second power. This will give us a completely new equation. Now when I square a square root, that cancels out, leaving us with 2x minus 3. And on the right hand side, we can square 9 to get 81. So this new equation, 2x minus 3 equals 81, contains the solutions to the original equation, assuming that the original equation has solutions. So we can go ahead and solve. We'll add 3 to both sides. We'll divide by 2. We get x equals 42 as a proposed solution. Again, this is a proposed solution. So now what we're going to do is we're going to check our solution. We're going to plug it back into the original equation. So we have the square root of 2 times 42 minus 3 equals 9. We can go to simplify. We'll get 84 minus 3. We'll get 81. And the square root of 81 is 9. So since this is a true statement, then we know that 42 is also the true solution to the original equation. Here, our radical is not isolated, so we need to get the radical by itself first. You don't need to write this part down, but I want to show you what happens when we don't isolate the variable, or isolate the radical, so that you understand why this step is so important. If I go ahead and square both sides of my equation, 0 squared equals 0, which is fine. That's not really the issue here. The issue here is that I now have two terms in this squared expression, which means I have a binomial squared. A binomial squared, again, we need to write as the binomial times itself. We can also use the formula for squaring a binomial, but this will help illustrate the point a little bit more clearly. Since I'm multiplying a binomial by another binomial, we can apply the distributive property. So then I have negative 10x minus 1 in the radical squared, but then I have to multiply over here. So I get 3x radical negative 10x minus 1. I multiply again, I have another 3x radical negative 10x minus 1. And then I have another multiplication that gives me 9x squared. So this first radical cancels out. And then my last term doesn't have a radical, but these terms don't cancel out, and I'm left with plus 6x root negative 10x minus 1, which doesn't help simplify this problem any. I'm still left with the same exact radical that I had before. So it doesn't really eliminate the radical unless we isolate the radical first. So let me erase all of this, and let's go ahead and start the right way. We'll subtract 3x from both sides. So we have negative x, or 10x minus 1 equals negative 3x. Now we can go ahead and square both sides of the equation. So we're left with negative 10x minus 1 equals 9x squared. And since we have a quadratic and not a linear equation, we want to go ahead and set our equation equal to 0. So we have 0 equals 9x squared plus 10x plus 1. Since it's in standard form, we can go ahead and factor. So we're going to factor by splitting 10x into 9x and x so that we can factor by grouping. If you're rusty on the factoring, you can go back to Unit 5 and brush up on the factoring skills from there. It's been a little while since we've used those skills, but they are necessarily important still. So we have 9x plus 1 and x plus 1. Now that it's factored, we can apply the zero factor property, set both factors equal to 0. So we get x equals negative 1/9, and we get x equals negative 1. Now we need to check both of our proposed solutions in the original equation. So we're going to start by checking, let's just do negative 1, that's the easier one to check. Negative 10 times negative 1 minus 1 plus 3 times negative 1 equals 0. So if we go ahead and do the radical part first, what we're going to end up with is the square root of 9. And then 3 times negative 1 is negative 3. The square root of 9 is 3 minus 3 equals 0. That's true, so we know negative 1 works. We can do the same thing, but we're going to check now with our fraction, negative 1/9. So we've got negative 1/9 and negative 1/9 here. So we can do the radical. Negative 10 times negative 1/9 is going to give us 10/9 minus 1. And then we're going to have minus 3/9. And we'll simplify that on the next step. 10/9 minus 1 gives us 1/9. And then we can simplify this to 1/3. We take the square root of 1/9. And we get 1/3 minus 1/3 does indeed equal 0. Since that works, we know that negative 1/9 is also a valid solution. So both of those are our solution. Here we have a cube root. Just like before, we want to isolate the radical. So we're going to subtract 5 from both sides. So we have the cube root of x plus 1 equals negative 2. We'll raise both sides to the same exponent. Since it's a cube root, we're going to raise both sides to the third power, leaving us with x plus 1 equals negative 8. We can subtract 1, x equals negative 9, and we'll check it in our original problem. The cube root of negative 9 plus 1 plus 5 equals 3. So the cube root of negative 8. The cube root of negative 8 is negative 2. When we add 5, that does indeed equal 3. So we have a valid solution of negative 9. Our radical is already isolated, so we're going to go ahead and square both sides to cancel the radical on the left. Now again, we're squaring a binomial. So this is x minus 2 times x minus 2. So when we apply our distributive property and then combine like terms, the right side is x squared minus 4x plus 4. Since we have a quadratic, let's go ahead and set it to standard form. We're going to subtract 4 from both sides. That'll actually cancel. We're going to add x to both sides. So 0 equals x squared minus 3x. Since it's a binomial and not a trinomial, the only thing we can do is factor out the GCF of x and set both factors equal to 0. When we solve, we get two solutions of 0 and 3. We'll go ahead and check both of those solutions to see if they're both valid. Starting with 0, 4 minus 0 equals 0 minus 2. So I have the square root of 4 equals negative 2. 2 does not equal -2, so we know that 0 is extraneous. X equals 0 is extraneous. So we're going to toss that solution out, and we're going to ignore it. Now let's double check 3, make sure it still works. 4 minus 3 equals 3 minus 2. So the square root of 1 equals 1. 1 does indeed equal 1. That is valid. So our only solution is 3. No need to even mention that x equals 0 is extraneous. Here we have two radicals. If we go ahead and just square it as they are, it's not really going to help clean up our equation that much. It will a little bit, but generally the easiest thing to do is pick one of the radicals and go ahead and isolate it. So we're going to subtract the root 2x and move it to the other side. So we have root 2x plus 5 equals 3 minus root 2x. Now we can go ahead and apply the power rule. That'll eliminate on the left, leaving us with 2x plus 5. And then using our distributive property, I'm squaring a binomial again. So we have 9 minus 3 root 2x minus 3 root 2x plus root 2x squared. So that gives us 9 minus 6 root 2x plus 2x. Now we can go ahead and combine like terms. So since we have a 2x on both sides, we can subtract and those will actually cancel. We can also go ahead and subtract 9 from both sides, leaving us with -4 equals -6 root 2x. And I prefer to also get rid of any factors outside of the radical. So I can multiply both sides by negative, or divide both sides by -6, leaving me with a positive 2/3 equals the square root of 2x. Now we can apply our power rule, and we'll square both sides, leaving us with 4/9 equals 2x. And then last but not least, we will divide both sides by 2, leaving us with 2/9 equals x. So we'll double check our solution. The square root of 2 times 2/9 plus 5 plus 2 times 2/9 equals 3. So we get 4/9 plus 5 plus square root of 4/9 equals 3. Here we can add those together and we get 49/9 plus the square root of 4/9 equals 3. And then we can take those square roots. So I have 7/9 plus 2/9, thirds. 2/3, 7/3 and 2/3 equals 3. And when we add those together, 9/3 does indeed equal 3. So we know that 2/9 is a valid solution. Last part here, we've got the square root of 2y plus 3. It's already isolated, so we can square both sides. 2y plus 3 equals 16. We can subtract 3 from both sides. So 2y equals 13. Divide both sides by 2. Y equals 13 over 2. Let's plug it back in to check it. This gives me 13 plus 3, which is the square root of 16. And the square root of 16 is 4. 4 does not equal -4, so 13/2 is extraneous. And since there's no other answers for us to choose from, we have no solution. Lastly, we'll just use a couple Pythagorean problems. This isn't going to be using the power rule explicitly, but every time we do radicals, it's a good idea to include some information about the Pythagorean theorem because exponents and radicals are closely related. So here we want to find the leg of unknown length of a right triangle if one of the legs is 4 meters and the hypotenuse is 10. So we're going to start by drawing a right triangle. And it doesn't matter which leg we label as A or B and which one it's going to be for. So we'll just say that this one is 4. B we don't know. And then our hypotenuse is 10. We always label our hypotenuse as C. The hypotenuse is the longest side. It is always opposite the right angle. So we can use our Pythagorean theorem. A squared plus B squared equals C squared. 4 squared plus B squared equals 10 squared. 16 plus B squared equals 100. Subtract from both sides, we get 84. And then in order to get rid of the square, I can take the square root. Those undo each other. So B equals the square root of 84. And since there's no rounding directions, then what we're going to go ahead and do is we are going to simplify this. So I can split this into 4 and 21. So B is equal to the square root of 4 and the square root of 21, which gives me 2 square root of 21 as the exact value for the length of leg B. For this last one here, we've got a 50-foot supporting wire that's to be attached to a 75-foot antenna. So I'm just going to draw a little diagram here where I've got this antenna station here, and here's the antenna up on top. Okay, and this entire tower is 75 feet tall. Okay, now the 50-foot wire has to be attached to this antenna. Now let's think for a second. If I try to attach it to the top and it's only 50 feet tall, then it's not going to actually reach the bottom. Okay, so it's not going to be able to touch the top, because even if it comes straight down at 50 feet, we're still going to be 25 feet short of reaching the bottom. So this cable, one, wouldn't be very useful if it was coming straight down, and it won't reach the ground if it's at the top. So it needs to be attached somewhere lower than the top, and it's going to come out to the ground. And specifically, it's going to be anchored to the ground 20 feet from the base of the antenna. That's based on the directions in the problem. Here, anchored 20 feet from the base of the antenna. So the distance from the anchor point to the base is 20 feet. So right now we see a right triangle that's being formed. And the wire that we're using is 50 feet long. So that's going to represent this hypotenuse side. So we've got our right triangle here. The question is saying how high from the base of the antenna is the wire attached. We are trying to find this distance here. So we could label that x or any other variable. So again, we can use our Pythagorean theorem. We'll say that a is x squared plus 20 squared equals 50 squared. That's going to be x squared equals 4 or plus 400 equals 2500. So x squared equals 2100. To get rid of the exponent, we can square root both sides. X is going to equal the square root of 2100. We can split this into 121. So we're going to have the square root of 100 and the square root of 21, meaning that our distance is going to be 10 square root of 21, which is approximately 45.8. Now it doesn't say to round, so this is our exact solution. Here is a rounded value to 1 decimal point when you pay attention to any rounding directions. Now the second part of the problem asks, if the local regulation requires the supporting wire to be attached at a height no less than 3/5 of the total height, have the local regulations been met? And so we have to figure out, is this distance more than 3/5 the total height? Well, to find 3/5 of the total height, we multiply 3/5 by 75 feet. And when we multiply those together, we get 45 feet. So, since this is at 45.8 feet, and 45.8 feet is no less than 45, we know that yes, the local regulations have been met.